What are they doing out there?
Anyway, welcome back to Element 14 Presents. I'm Clem, and I think I should teach you a valuable skill. Reverse engineering random gadgets to use them as Arduino modules, because you never know where you get your stuff from in these days. Depending on when you watch this video or when it comes out, things don't always work like in a continuous fashion. It might be a bit difficult to get certain parts. So I think you should know about reverse engineering random things. For this episode, I chose this random cheap gadget and we are turning it into an Arduino compatible module. But the process should work on almost anything. You may or may not have the parts that you need for a project already around in your workshop. Or maybe you have a device at home that has the part inside. You could salvage that. But sometimes you just go out and get some cheap gadget that may have the right properties for your project. In my case, this is a breathalyzer key fob. So it's not really a really good breathalyzer, but it's enough to tell if there is alcohol present or not, if it's more or less than before. So for a project where you just need to determine, hey, is there alcohol mist in the air? For example, if you used isopropyl alcohol to clean your 3D printer, then you could turn on and off a fan dependent on the alcohol contents in the air. Even make it adjust its speed proportionally to the measured alcohol. That might be a useful project, and for that we could just salvage a thing like this, but also make use of its internal properties. So this cost me just a few bucks, and it will only cost me a bit of reverse engineering, and you can follow along. To make something Arduino compatible, we have to make it possible that it can interact with an Arduino. That means we have to have compatible pins, compatible voltage reference levels, compatible power supply, and we have to have a way to determine what's actually going on in there. So in this case, we have a case in key fob fashion and a button on the upside and another on and off switch on this side. First, we have to figure out how these things work. And that's the easiest way to do that is by popping in some batteries and just trying it out. The batteries are in. If we use the on and off switch on the side, this just enables this red LED. It doesn't seem to do anything else. So this is maybe just a light so you can find your keys or whatever. So if I press this one, it lights up various LEDs. And now it goes to green. I breathe in it. Okay, there's no alcohol. It's still green. Okay, let's do the same thing again, but this time I have isopropyl alcohol with me. Is it ready? Now it's ready. Now come on, spray. Oh yeah, it has detected the alcohol mist. So the modern wipe coder way would now be to write an AI agent that uses a servo to press on the button and look at these LEDs with a detection model and determine which ones of these light up. And so you can basically remote control the device. But we're not wipe coders on this channel. We're old school and build things that actually work. So we take this apart and see if we can make it directly electrical Arduino compatible. Inside here are two AAAs, which means this thing runs on 3 volts. I can now determine how much current it needs by just replacing these batteries with a bench power supply and just measuring the current draw while it's in use to determine how much juice this actually needs. Also, curious thing is when you just start it, it needs kind of a startup sequence or delay. Maybe that's to prepare the sensor for a reading. And it seems to now take longer than before because I've sprayed it with alcohol. So maybe it waits for this to, like, all the alcohol to go away before it can actually measure. So I expect in here to have a microcontroller, likely in a glob top fashion, so it's directly on the board and some epoxy over it. so it might be a bit difficult to interface, but we're still gonna try. When we remove the electrical components from the shell, we can quickly see, hey, this is a one-sided board, which is really great for reverse engineering because there are no hidden layers on the inside. There are not even layers on the backside that we have to take into account when we are tracing traces. So this is a great example, or basically a great way to learn reverse engineering with a one-sided board. So if you do this for the first time, try to get a gadget that just has a one-sided PCBs. The very cheap things on the market usually try to avoid as many layers as possible. So it wouldn't be too hard to find a thing that has a one-sided PCB, so you learn how to trace all these traces. And I traced all these traces and I found a few peculiarities about this board. So I expected this thing to have a glob top ASIC, likely, because mass-produced gadgets usually have very cost-effective solutions for very, very big production runs. But this doesn't. In fact, it's not even a microcontroller. It's an LM339. That is a quad comparator chip by TI. I might even have one of those in my hoard. So I'm sure I have a quad op-amp and a quad comparator maybe somewhere in there. So it's actually a standard part that is used. So this makes the curious case of these procedures before it actually measures a bit more interesting, because how do they do that with just a little comparator chip, and there seems to be like a few resistors and a cap, and I've seen one diode on there and a few LEDs. So that might be quite interesting. We have to draw up the schematic, at least the big portions of the schematic, to understand how this thing actually works. To KiCad. Welcome to KiCad. This is a crude schematic of the thing. So the most important thing is that you basically get the block diagram right. You don't have to know every value of each component. The main ones will help you, but the most important thing is that you know how stuff is connected in general, so you understand the function of something. So this is, don't take this as gospel as the exact schematic of the thing, but this is, I think, pretty close. So one thing we have here is batteries, of course, connected between ground and 3 volts. These are two AAAs. We have this LED over here, which is just connected to power over the switch, so nothing special here. But something special here, we have an LM339. This is the way you draw logic gates and similar stuff in schematics. You don't use the full chip, you use the functional bits, and it's split up into each of its functional bits because each IC has multiple of these function blocks, basically. So this LM339 quad comparator IC means there are 4 comparator circuits inside. Each of them can work independently, or you can daisy chain them or put them together in various ways. In this case, a lot of them are connected to each other. The first one that is the most important to us is this one here. So I've traced basically where all the traces go and used the multimeter to beep out some connections in between these individual components. Sometimes I had to remove one to see where it actually goes. For example, the switch I had to remove to see, oh, it actually goes back down here. Some parts of the layout are a bit confusing, but I think I figured it out. So this here is basically a time delay circuit. It's basically based upon the discharge rate or the charge rate of this capacitor. And once this passes a certain threshold, then power is activated over here. And that means over here we can activate this transistor, which in turn activates the sensor. And that allows us to make a sense from a measurement from this sensor. So it all makes sense. In the normal device, this is then put into a comparator, and this is basically only activating after the preheat phase. So then pin 5 here is connected to another comparator, whereas pin 5 is over here, over a resistor, and this activates the next LED. So as long as this is pulled high, I think it's the yellow LED will be lit on, and only if that has fully discharged, then the green LED, this one, will light up, and that means we're ready for measuring. So these are basically all dependent on a time constant over here. That might change with temperature because it's not temperature compensated. It's all fixed resistors. So it's basically a crude way of having a time delay. It can be quite exact, but it's not like variable on some other factors. So it basically just waits for the thing to heat up. And if that goes below a certain value, then it will activate all the rest. I think this is a quite good way to do it, and it's certainly a very cheap way to do it. It's for sure also not the best way to do it, but it's one way. And it's a way that we can interact with, because we now only have to have two connections. We have a typical current draw of 26 milliamps, but if we remove the LEDs, most of that goes away. I couldn't really determine how much it is. I don't have the right kit for that, but it's certainly below 10 milliamps. So we can safely source the power we need directly from an Arduino pin. And we have to interact with these in two ways. The first one is we have to read the sensor over an analog pin. And the other thing is we have to enable the circuit. And the important thing here is we need to have a voltage divider, because our Arduino will give 3.3 volts, or if you use a 5-volt Arduino, like an Uno, then it will have 5 volts. So we have to have a voltage divider that puts that down to 3 volts. And we have to have exactly 3 volts, so it still exactly works as intended. If we would change that voltage, we would also have to change all the resistor values on the board, which we don't want. In this case, we only need 2 additional resistors. And here I've imported an Arduino Shield pin out. And if you download the files on element14.com, you basically now have the exercise to determine which 2 pins you can connect to these pins, and then turn the whole circuit into an Arduino Shield, if you want. So this is a little free KiCad exercise that you can take on if you want. I've made some assumptions about the board design. I expected this quad op-amp to have one stage acting as an amplifier for the actual sensor, and then the other ones would basically determine which LED to activate depending on the level. Turns out that's not the case. One of the stages acts as a delay for the boot up. So it waits for the sensor to cross a certain threshold in its output before it actually activates the other stuff again. This is basically like pre-warming it. And looking at the datasheet of these types of sensors, I didn't find the exact ones, but they work very similarly. They basically have to preheat to make sure that everything evaporates out of the sensor, and then they take a new measurement. So this preheating is done with an RC delay circuit. Once that has completely discharged, the first comparator lets the other ones engage. And that is also how it switches from the yellow LED to the green LED to indicate it's ready. So that's quite an ingenious circuit, I think. And we can use that to our advantage, because either we let this thing heat up on our own, or we just rely on these the circuit inside. And I think it would be easier to have the circuit inside do the warm-up in sequence that we know works, and in code we tell it to do the warm-up, and we determine when to do a reading, which is a lot more flexible than just having to do everything manual. Also, but in that case we could use just the sensor alone and just detach it from the board, but I actually want to take advantage of this circuitry. So how does the activation of the circuit works? It's not like everything is powered and you just hit an enable line. No, the unit actually is not connected to power when it's not actively in use. That means your push button is actually just closing the circuit. so it enables power to everything at once. That lets this RC circuit charge and lets the sensor preheat. So this is my enable line. So the enable line has to supply all the power for the whole circuit. If we measure how much power that draws, we're in a range of about 26 to 12 milliamps depending on the status. The highest I found was 30 milliamps, which would still be enough current draw to damage some pins on some microcontroller boards. Usually Arduinos can provide up to 40 milliamps in syncing, but not in sourcing. And this is, we have to source current. So I have to get rid of a lot of current usage. The easiest way to do that is just by removing the LEDs. We don't need them anyway. So I have removed all 3 LEDs. I'm doing the same experiment again, and now it doesn't show any current usage. Is that because it doesn't actually draw current? Could be my wiring is a bit wrong. We have to double check that. But turns out it draws current, but it's so little, my power supply can't measure it on its own. So we would need something like a very precise multimeter, or there is the power profiler kit from Nordic Semiconductor. That is also available on Farnell, by the way. This is a very handy tool for analyzing power situations where it goes below a few milliamps. So if you really need to know how much current does something draw in deep sleep or whatever, use a tool like that. For ours purposes, it's enough to know it doesn't draw nowhere near 20 milliamps. So that means we can power the whole circuit directly from the Arduino pins. I don't even have to have a direct power supply. This makes interfacing it as an Arduino module a lot easier. So if you can do it that way, you might want to, but check the power requirements first. I want to use my module with Arduino. In this case, I'm using an Arduino MKR Wi-Fi 1010. Handy board with Wi-Fi connection on there. I used that in a few previous projects. This one has 3.3 volt logic levels. Our device runs at 3 volts, so there is no way we could fry the pins of our board. We checked the power consumption, so it's fine to use it. You could also use a Raspberry Pi Pico. You could also use a 5 volt microcontroller like an Arduino Uno. The only trouble with that is the logic levels would work, but you can't directly supply from a pin. You would need a voltage divider in between. And turns out you also need a voltage divider with the 3.3 microcontrollers, because 3.3 volts and 5 volts are not the same as 3 volts. And these 3 volts are important because all the resistors on our board that we reverse engineer, they are also dependent on the voltage that they were intended to work at. So 3 volts. If you still want something to work the same way, use the same voltage. So we already need a voltage divider. If you use it on a 5 volt microcontroller, you just change the divider values. To get a voltage divider from 3.3 volt to 3 volt, that's very easy. You just need a 100K resistor and a 10K resistor. It just has to have 10 to 1 ratio in between those. These are very common resistors. This gets you to 3 volts exactly. For 5 volts, you can make the exercise at home or use one of the online calculators to determine the resistors that you need. Once you have that in place, you're basically good to go. I've used a little perf board to solder up my circuit. So we are connecting to the ground, to the sensor sense line that goes into the comparator. I initially thought it was amplifying the signal first, but it doesn't. That's just the stage where it preheats in the first comparator stage, basically. So I go directly from the sensor to the Arduino, but then I power the whole circuit via another Arduino pin that I can digitally control over a voltage divider, and that activates the circuit. So the whole charge discharge stuff exactly works on the original thing. We just interact with it digitally with an Arduino. This one, to be exact. Only thing that's left is a bit of code to make it work. Welcome to the Arduino IDE. Here is my first example code for our new gas sensor module. The sensor should only react to stuff like alcohol, it doesn't really care if it's ethanol, methanol, or isopropanol. It just gives you a different measurement depending on how many of these contents are in the air that it can reach, basically. So first thing is I'm using an Arduino Maker Wi-Fi 1010 in this case. This is because it's a 3.3 volt Arduino. If you use a 5 volt one, you still can, you just need to change the resistor values that we have on there. So I first determine which pins I need to interact. Important, the sensor read pin has to be an analog capable pin. The enable pin can be any pin, it just should be able to source a bit of current. We initialize serial just so we can get a reading out of that. And here is a function that just meets read and print sensor. It's this function here. So first I want to know, is this the first time in the loop that I call the sensor? Because in that case, I need to warm up the sensor. So I need to rely on that time delay. So as long as it's actually warmed up, I can still use it. The unit itself will warm it up on any activation, which means it should be warmed up every time we're using it. We just need to first let it warm up on the first call. That's why we do this only once. Any subsequent reading should already be good. So we let this run for about 10 seconds. Why 10 seconds? In the datasheet of these gas sensors, not the exact one that I have, but they are pretty similar. It says you should warm it up for about 10 seconds. That's why I did it that way. We also just enable it. And then here are some variables for the interval counting. So we take measurements over 1 second, then we average these measurements. Because they're analog measurements, they will be a little bit jittery, and to avoid that jitter, we basically make a lot of measurements, average them, and then print out only that one measurement. You won't get any faster readings than in 1 second for gases anyway. So why overcomplicate things? And that just means if there is an average that's bigger than 0, so if we have a new average, then we just print out that. And that means we can see how the unit measures stuff in real time, basically after the first initial warning. It's that easy. Now that we have some working example code, we can now use the functions that we program to read out the sensor. We can programmatically preheat the sensor, take a reading, graph that on the serial monitor as a plot, or just get the values, pump those in additional values. We're basically ready to use our gadget in any Arduino project. This did just cost us the gadget itself, which was a few euros, 2 resistors, and a little bit of brain power. I hope you do the same with whatever you find, maybe on the street or in a parts bin. So where's the difference between just salvaging components, buying them online, and reverse engineering? In practice, not much. You just have to do it to get your parts. If you want to download the schematics for this project, it's on the Element 14 community. You can also go there to interact with me and all the other hosts, download all the files for the projects, and just generally have a lot of fun with project videos and other creatives. I gotta go. I need to put this thing back because I needed like a speed sensor, but then another project is waiting for me.